So let's continue with our discussion of hemostasis, that is, the stoppage of blood flow out of the cardiovascular system. We first talked about vascular spasm, that's constriction of the blood vessel to slow down flow. And then we talked about the platelet plug formation and the events that lead to that, factors including von Willebrand factor, ADP, thromboxane, A2, serotonin release, calcium ion release. And now we're going to move on to the longer chemical fix. And remember, this whole process is a positive feedback mechanism, meaning that if something like vascular spasm doesn't happen, or if we're missing a chemical that's part of platelet plug formation, then we can't get to the rest of the entire process of hemostasis. So hemostasis can occur, or I should say coagulation can occur under two directives, the intrinsic pathway or the extrinsic pathway. So the intrinsic pathway is stimulated by damage to the endothelium of a blood vessel. That is going to expose collagen fibers, tissue factors, or von Willebrand factor. It will also stop the formation of nitric oxide and prostacyclins that prevent coagulation from occurring. It uses chemicals that are intrinsic in blood. It's a slower process, but it's simply a different way to get to prothrombin activator. The extrinsic pathway results from damage to tissue cells or anything that is near or close to those blood vessels. Those cells will release tissue factor or an extrinsic factor, factor 3. It's a faster mechanism, but still results in the formation of prothrombin activator. Often in tissue damage, you'll see both of these pathways activated. As you can see in both, there are multiple factors designated by Roman numerals. These are clotting factors, protein factors, that generally serve in their activated forms as enzymes for the formation of future factors that are enzymes for future factors. We also see calcium as part of the coagulation cascade. And what you don't see here, but what is also vitally important, is vitamin K. And vitamin K is produced by E. coli in the large intestine, or can be obtained from dark green leafy vegetables. And vitamin K is required to synthesize many, specifically, of these clotting factors. Tissue factors, remember, are released from damaged or exposure to the tissues deep to the endothelium. At this point, we should also discuss hemophilia. So there are several types of hemophilia, the most common, most deadly of which involve a lack of factor 8. And in that case, that is a genetic sex-linked or X-linked disorder that generally occurs in boys and results in easy bruising and inability to clot and life-threatening hemorrhaging potentially if clotting factors aren't induced via injection. Hemophilia B is due to a lack of factor 9, and hemophilia C is due to a lack of factor 10. But since these two are farther down in the clotting cascade, they seem to pose lesser dangerous symptoms. The second phase of coagulation uses that prothrombin activator created in phase 1 as an enzyme to create activated thrombin. The activated thrombin is used as an enzyme in two places in phase 3. The first one is to convert fibrinogen into fibrin, which we see here in that fibrin mesh or fibrin net, these sort of beige lines here, captures the platelets and creates sort of a sea net or a fish net in which the platelets are trapped. The fibrin is then going to contract, pull all those platelets closer together, pull the fibrin proteins closer together, and create a very neat and compact clot or scab. The second place we see that thrombin serves as an enzyme or an activator is here in the formation of those cross-linked fibrin meshes. And that part of the cascade also requires calcium. So let's look at that in this animation. Here you can see the fibrin being laid down. And the formation of the cross links. So as this clot retracts, those fibrin proteins are going to pull tighter and tighter, pull the platelets closer together. That is going to cause extraction or squeezing out of serum, the liquid part of blood, from the clot and leave that fairly solid clot. Now, some chemicals that are released from the platelets, including PDGF, are going to stimulate the smooth muscle cells to regenerate themselves. And another chemical called VEGF, vascular endothelial growth factor, will stimulate reproduction of that endothelial membrane. And this happens within about 30 minutes to about 60 minutes. Now, the last phase of coagulation, of the healing part of coagulation, is fibrinolysis, which refers to breaking up of that fibrin net. And that starts within a day or two after the original injury. So in this case, plasminogen, a precursor to the enzyme plasmin, is converted into active plasmin with a few chemicals released from those platelets, including factor 12, thrombin, which was formed during the clotting cascade, and TPA. So let's look at fibrinolysis in this animation. Question 17. What events or chemicals trigger step 1 of hemostasis? That's vascular spasm. Question 18. Describe step 2 of hemostasis. That's platelet plug formation. And your answer should, of course, include the goings on at a cellular and chemical level. Question 19. In step 3 of hemostasis, this is coagulation. List the 3 broad phases of this process. 20. What's the difference between the intrinsic and extrinsic pathways to prothrombin? Please be as specific as possible. 21. Which 2 reactions in phase 3 of coagulation are catalyzed by the product of phase 2 coagulation? And question number 22. There are numerous chemicals involved in the clotting cascade. List the functions for the following players in the coagulation cascade. PF3, calcium ions. Factors on a general level: vitamin K, thrombin, fibrinogen, prothrombin activator, and fibrin. 23. Why, when, and how does clot retraction happen? 24. Why, when, and how does fibrinolysis happen?